Yes, today we're going to look at Quebec OSCAR100. Easy way to at least start monitoring it, because I still believe that you first need to listen before you should start transmitting or taking on the next step that is now transmitting. So lots of this information OSCAR100 has been around now for a few years, but maybe it's a good thing sort of to revise some interest in the satellite and to get some more people on board. If everything is presented in one single presentation, then hopefully it will also get some more enthusiasm going for it. So this morning, going to look at the background. Where's Quebec OSCAR100 coming from? History behind it. Also, dynamics of geostationary orbits. That is also very interesting, seeing that we're talking about the scientific hobby space and everything that's applicable to it. Going to look specifically at the narrowband linear transponder. Of course, there's also a wideband transponder that allows you to transmit and receive video signals. And Gary, Z6 Yankee India, is, I think, our specialist in that field. He's been quite active on it. And then the possible ground station solutions, easiest way to at least receive the signals from the satellite. So yes, let's start with ISHL2, the background. Now the Qatar satellite company, which is known as Ishelsat, launched their second satellite, now named or referred to as ISHL2, on a SpaceX Falcon 9 rocket on the 15th of November 2018. So that's nearly 4 years ago already that this satellite was launched. It was meant to be launched in 2015 already, but yes, as we know, especially with space, everything gets delayed along the way for various reasons, mostly technical performance and cost, etc. So it was delayed for 3 years, but then eventually it happened, and I think to the big relief of everybody involved. Commissioning and maneuvering took more than 2 months to complete, but yeah, that is actually relatively quickly in terms of satellites in space. To check out the whole satellite, get everything in place, and sort of declare it operational, that it can start to earn revenue. Yeah. So it then became operational in February 2019 and has been running quite smoothly since then, with some enhancements along the way as well. They're seeing that it's software-based, easy to upgrade, everything that is possible with the software or coming with software. So important one here is that the Qatar Amateur Radio Society managed to secure the privilege to have an amateur radio payload on ISHL2. Now, privilege is about the correct word there, because it saves us a lot of, or the radio amateurs as such, a lot of effort, money, and everything that goes with it, launch opportunities, if you can piggyback on somebody else's satellite. So you just reap huge benefits in the process, that you don't need to develop the whole satellite, everything that goes with it, pay for the launch, etc. So when it became the narrowband transponder became active, or actually both the narrow and the wideband transponders became active, it became known as Qatar OSCAR, or Quebec OSCAR100, so people refer to it. So that was the 100th amateur radio satellite in space. That in by itself is already quite a milestone. So if we look at geostationary orbit, what it all entails, it's a circular orbit above the equator. That's the only place where you can get a geostationary orbit functioning correctly. So the orbital period is equal to the Earth's rotational period. The implications of that is that for somebody on the ground, the satellite appears to be motionless. In other words, it's always at the same spot in the sky. Once you've aligned your antennas, you don't need to touch them again. No need for tracking, automatic tracking, elevation, azimuth adjustments, or anything like that. the antenna is always pointing at the satellite. So it's a very convenient, call it a very powerful orbit as such. And it can only happen at an altitude of 35,786 kilometers above the mean sea level. Now that's quite different to our other satellites, our low Earth orbit satellites that are 350 up to 700-800 kilometers above the Earth. So this is quite a distance away. Up to Quebec OSCAR100, the previous high altitude amateur satellites were in a highly elliptical orbit, and that is to increase sort of the coverage or the time on station. But these orbits didn't always favor South Africa, seeing that the satellites were built by the people in the north, Europe and the USA. Of course, they engineered the orbit so that they've got most access to the satellite. Which makes sense, of course. So the satellite would, call it, hover above Europe or the northern hemisphere and then race past the southern hemisphere just to be hovering above the northern hemisphere once again. These satellites were known as Phase 3 satellites, and the history behind it, Phase 3A was lost at launch, Phase 3B became known as OSCAR-10, 3C became known as OSCAR-13, and 3D was OSCAR-40. But that is quite some time ago. That was OSCAR-40 operated from 2000 to 2004. So it's about high time that we got access to another high altitude satellite with all the benefits, the very big footprint, enabling you to communicate much further than just, say, locally around South Africa, so that you can reach Europe and all of those other places as well. Now we've moved on to Phase 4, which is now the geostationary satellites. At this stage, Quebec OSCAR100 is known as Phase 4A, and it's currently the only geostationary satellite, although they are mentioning lots of rumors about some more geostationary satellites planned for the future. Americans are building or working on a geostationary satellite, and I think some other countries as well. I was actually expecting some to become more active, or some to become active quite soon, but yes, things in space don't always happen as what you expect. It takes much longer, as we've seen in the past. Interesting aspect from geostationary orbit is the beam width or the antenna gain that you can implement on your satellite. Too high an antenna gain actually provides spot beams, and then you haven't got global coverage. For our type of satellites that you want to get maximum coverage, you are limited to about 20 dB of antenna gain. And yes, over 35,000 plus kilometer orbit, 35,000 kilometers there, 35,000 kilometers back. Some more gain would of course have been nice. But yes, that is what the physics are dictating to us. Quebec OSCAR100 is in a geostationary orbit at more or less 25.5 degrees east. So that implies that it's basically straight right true north from us here in Johannesburg, Pretoria, and say most of South Africa. So it's a very favorable orbit for us, a very favorable position. Something that we're not quite used to, seeing that the previous Phase 3A satellites, etc., were more orientated for the people in the northern hemisphere. If you look from that, the Google Earth picture, it covers actually a huge amount of the Earth. If we look at it slightly differently, the footprint that we are looking at there in the west, it is basically Brazil, and then all the way in the east, Taiwan, to the north, way into Russia, whole of Europe. So it's a huge, massive footprint. You can see the little cross in the middle. That is the position, more or less the position of OSCAR100. So very favorable for us in South Africa, and that's making our life, of course, very easy as well. So it covers a population of 5.2 billion people. That's a huge percentage of the Earth's population. Of that, those people, 1.5 million are amateur radio amateurs. At least 225 DXCC entities for the people that are chasing that. And then, as we've mentioned, the footprint from the east, Brazil, all the way to Vietnam in the east, Brazil in the west, pardon for that one. Does not include mainland USA, for better or for worse. That's actually quite an interesting one. So hopefully when the Americans do launch their own geostationary satellite, it will at least enable us here in Africa to communicate with them. That would be quite handy, quite something to do. If we now look at the narrowband linear transponder, it's the one that we communicate through, easiest for starters, built by Elsat DL in Germany. The frequency range for the uplink, 2.4 gigahertz to 2.4005, so it's a 500 kilohertz or half a megahertz bandwidth that we've got available to play with. Center of the band thus is 2400.250 megahertz. It's quite easy to remember the figures there. Here from the Earth, right-hand circular polarization is required if you look towards the satellite. But remember, if you're not using a dish antenna and you need to feed the antenna, then you have to use left-hand circular polarization, because the moment it's reflected by the dish, it swaps the polarization around and then it transmits the right-hand circular polarization. So if you're making a helix that you're going to use in conjunction with the dish, keep that in mind. It's like looking in a mirror where your left and your right get swaps around a bit. Downlink frequency is on 10 gigahertz, at the top of the 10 gigahertz amateur band. In the past, 10 gigahertz were also referred to as X-band in military terms. So 10.489 gigahertz, 0.5 to 10.490 gigahertz, right at the top. The signal from the satellite makes use of vertical polarization, which is actually quite handy, that you don't need any special or fancy receive antennas, or when you're using a dish antenna, no swapping around of the polarization either. The preferred modes are what we are used to on the lower bands, narrow band, in other words, SSB, CW, and then all our common digital modes. The satellite transponder was very well designed, especially regarding the sensitivity, noise figures, bandwidth, everything that's required there. And with less than 5 watts into a relatively small dish, that's 60 to 75 centimeter offset dish, that's your typical DSTV type of dish that you've got available here in South Africa. I think the minimum size at the moment that's easily obtainable is about 80 centimeters, or referred to as 80 centimeters. So you need very little power actually to access the satellite and to successfully communicate through it. Most people probably use between 1 and 2 watts, and no problem there. Signals are quite good. Talking about the power levels, there's a limiter implemented on the satellite, referred to as Leila 2. My German not very good, but it's Leistungslimit Anzeige. In other words, it is monitoring your signal level that you are transmitting towards the satellite. And if you exceed a predetermined level, in other words, if your signal is too strong, then this lady becomes quite upset and puts a carrier on your signal, attenuates it, all sort of reaction like that to ensure that you're now not overdriving the satellite. And then, the AGC, automatic gain control of the transponder, kicks in, reducing the gain, and then the people using lower power gets pushed down into the noise, which is now not making it nice for anybody else. So Leila ensures fair play. That is the main thing behind it. And it makes life actually quite easy for us. No competition about who's the loudest and the strongest signal, that type of thing. So in short, running higher power than what's absolutely necessary is counterproductive, but that's also part of our license agreement, if we can call it that radio amateurs should use a minimum amount of power to ensure successful communications. The band edges are indicated by beacons, once again very well thought out. There's a CW Morse code beacon that indicates a lower band or lower edge of the band. In the center of the band, PSK400 beacon, same format is that was used on OSCAR100 in the olden days. In the past, it used to be the top of the band, but now lately or some time ago, the band has now been extended or doubled. So now this beacon is in the center of the band. And then there's a very interesting experimental beacon at the top of the band. And some very nice software, powerful software available to demodulate this beacon and to allow you to communicate through the satellite using some of interesting digital modes. So what you aim for is that your downlink signal should be as strong as what the PSK400 beacon is. If you exceed it by too many dBs, then Layla will it will catch her attention and she may become unhappy with you. So the PSK beacon level is now sort of the new 5.9. If you aim for that, adjust your power level to be equal more or less to that beacon level, the new 5.9. And that is more than good enough. Here's a picture of the band plan. It's available from the German website and all over the internet, but it's interesting to see. Left-hand side, we start with a CW beacon, then only Morse code, narrowband digital modes, SSB all the way up, mixed modes and special purpose mode. And then lately, there's contest portion of the signal of the satellite also added, as well as an emergency channel in case some global communications are required, then the satellite is available for that as well. That's part of our sort of community service from the radio amateurs. Now we're going to look at an easy way to start receiving the satellite, low cost, low effort type of approach to it. No need to build exotic X-band down converters. You can buy a DSTV LNB for a very good price lately. Lots of outlets, resources, and it's actually a very good candidate for our receiving station. You select by supplying the correct voltage, 12 volts power supply to this LNB, select the correct local oscillator. So no need for 18 volts or 20 volts, 24 volts or anything like that. Your normal 13.8 volt power supply in the shack is once again quite adequate. Nothing else needed to buy. So the IF that is then at the output of this LNB, the IF frequency is just below 740 megahertz. And yes, that of course is not close to any of our amateur bands. Your 70 centimeter band or 1296 band, 96 megahertz band, it's way sort of in the middle between all of that. But that's not a problem anymore. We've got all these SDR, software-defined radio solutions, and you've got RTL dongles, and from that going up to the Merix and other higher quality SDR radios. So SDR dongles is quite popular, and nowadays I think about every ham shack should have at least one of them, if not more. Advantages of a SDR approach is that you now can see the spectrum, see where the activity is. There's a waterfall display as well. Waterfall is a history over time where signals occurred, where somebody was calling CQ, for example. So you can go click on the frequency with your mouse and the receiver is tuned there, as simple as that. So this is quite convenient compared to the olden days where you had to turn a knob up and down, left and right. Although some people still like to do it, I think it's part of our legacy. This click and tune is very convenient for quick reaction, getting to a activity quite quickly. So what the receiver chain is going to look like, you're going to start with your dish. I've experimented, even something like this very small 30-70 centimeter camping dish is quite adequate for receiving downlink signals. Then you've got your 10.5 gigahertz down converter, which is actually now LNB. Then the only thing that you can sort of make yourself, although you can also buy it from Anton's website, is a BIST or your DC injector that uses a coax to supply power to your LNB. It's the same setup that your normal DSTV decoder is operating on. You've got your SDR, which in this case RTL dongle, and then you've got your computer or your laptop, and then some software that will perform the SDR, the demodulation applications. In other words, showing you the spectrum and the waterfall and demodulating SSB signals as well as the digital signals. So if you look at that, about the only thing that you require that you probably haven't got lying around or can easily get your hands on is a BIST or the DC injector. So very simple, very low cost. Here's a block diagram of the what's inside, what a typical LNB, low noise block, low noise down converter looks like. Start at the left with your feed on, and then it's got two polarizations, vertical and horizontal. The satellite transmits on vertical polarization. And fortunately for us, vertical is also selected by your 12-volt supply. So no problem there. You can basically just mount the LNB in a vertical position, aim it very close to north, and you should be able to see the satellite. So it's basically a plug-and-play effort. The 9.75 gigahertz local oscillator also being automatically selected with the 12-volt supply that you are going to use or feed down the coax. Now, if we look at some options for LNBs, suitable options, I'll start with the more exotic ones, the Avenger. Some of these are a little bit more expensive and basically intended for Europe, some other markets. What you'll see here is a noise figure claim 0.1 dB. Now that is most probably a Chinese specification. We would wish for 0.1 dB noise figures, but I think in reality the noise figure should be just below 1 dB. So take that with a pinch of salt, but I see everybody's doing it. But the 1 dB noise figure is more than adequate to receive the satellite. Another one that's especially popular in Germany is the Octagon. The Optima is what I've got here. And once again, they conveniently claim a 0.1 dB noise figure. And then the gain, 60 dBs to 65 dBs. Some other people claim 40 dBs. In general, all of that is more than adequate to receive the satellite with no problems. More locally available, we've got Elsat, this LNBU, the high stability, indicating that this is a phase lock loop based LNB, and not like in the olden days where you had some other free running oscillator, a SAW based type of oscillator or a DRO oscillator that was not adequate for SSB reception. This high stability indicating phase lock loop, that is the way to go. And I think the majority of LNBs that are now currently available in South Africa are actually the high stability type, LN with the phase lock loop type. Another option is the Aerial King. There are many Aerial King outlets around South Africa, especially in the bigger cities. And if you walk in there and have a look at their LNBs, you'd be surprised that sometimes the price, pleasantly surprised. Depending if they've got specials or not, you can expect to pay less than 100 Rand at times for a very high-tech LNB such as this one. The more recent one is this one in the black package, that single universal 40 millimeter LNB, 40 millimeter indicating the mounting size, but all the dishes that's available here in South Africa make use of the 40mm sort of throat. One thing to say about this LNB, the components inside are extremely small. So if you are planning to one day modify the LNB for local oscillator injection, higher stability, etc., this one is extremely small. You're not going to have fun trying to modify it. Some of the older versions using slightly bigger components are much easier to work on. Looking at the circuit diagram of the BISD or the DC injector that's required, once again very simple. Start at the bottom, 13.8 volt DC, that is your typical shack power supply, 100 picofarad decoupling, inductor to separate the RF from the DC. Oh, don't forget the idiot diode, the one in 4007, in case you get the polarity wrong, that you don't do any damage. And then on the left output goes to the LNB, making use of the F-type connectors, very cheap, R1 or R2 per connector, using normal low-cost TV coax as well. And on the right, you've got the DC blocking capacitor, 100 picofarad, goes into your coax that will eventually then go into your RTL dongle. And that coax run's not very important, enough gain in the system. I've managed to actually receive the output of the LNB without the connector being connected to the dongle, just using a small piece of wire to give you an indication of the signal strengths involved. This is now a homebrew bias injector. On the left hand side, you've got your F-type connector that's used by the video standards. Decoupling inductor, simple 10 turns around a 5mm sort of drill bit. Your idiot diode, and I've now used a SMA connector to feed a short coax run to my dongle. So simple as that. All of that built on a piece of Vero board, and that's quite adequate. Nothing critical in manufacturing or building your own BISD. An example of a low-cost RTL dongle. You typically don't use the remote and you don't use the antenna. You're only interested in a little, the dongle as such on the right-hand side. Looks like a memory stick. And yes, software, quite easy to get hold of. My favorite software is SDR console, allowing you to actually lock on the 400, the BSK400 beacon. If you look there at the spectrum in the center of the display, you can see there's a noise hump. So this indicates that I can't improve much on the sensitivity of my receiving system. That is a transponder noise, and even if I add more gain with a bigger receiving dish, it's only going to increase the noise, okay, and increase the signals as well, but the signal to noise ratio at the end of the day is going to remain the same. So this is quite adequate. The moment you can see that noise hump at the bottom, you've accomplished what can be accomplished. And you can actually, if needed, use a smaller dish, because I've got too much gain in the system already. On the right-hand side at the bottom, I've now locked onto this BSK400 beacon, but you can see there are also some sort of visual modes that the people transmit, and on the waterfall you can see the call sign and the person sometimes calling CQ, etc. over here. Okay, a possibility is to, if you further want to increase your down or your earth station, is to make use of sort of locking your LNB onto an external reference, or by feeding it an external 25 megahertz reference, because all the LNBs, the modern ones, make use of a 25 megahertz crystal inside it. So that is possible, but SDR console already locks onto the beacon, but some people feel that they want to do it sort of mechanically as well. And you can feed a 25 megahertz reference down the coax as long as the DC, or as well as the DC, and then the signal coming back as well. But that means that you have to modify your LNB. A good source for 25 MHz reference is the ADF 4351 synthesizer board that you can also use on the transmitting or the uplink side. So that's just something to keep in mind, but it's a little bit of a more advanced application. Locking onto the beacon is actually quite adequate. You can, of course, also look on the internet, listen to the satellite on the internet, various SDRs available. This one from Anton, for example, that you can actually enjoy the downlink without having to put up an antenna or anything else. Just use the internet. So that's definitely also an option. If we look at possible uplink solutions, so you've now got your downlink working well, you can monitor all the beacons and listen to all the activity. The next step will be, let's try and transmit, get the station together. This is a little bit more complicated, more advanced, not that easy to achieve with off-the-shelf components, but of course very doable still. We'll start with common radios that you've got in the shack, for example, the ICOM series, 706 and 7100 and 7000, etc. Just keep in mind that the AGC or the ALC isn't very good on those radios. That the moment you transmit, the first burst is high power before it then starts to regulate the power from the radio. So we're looking at, say, 10 watt, which is quite a common output on 2 meters. And we use this as the basis for the transverter or the up converter to get us to 2.4 gigahertz. So we'll use a modern approach as described by Whiskey 1 Golf Hotel Zulu on his excellent website on the internet. So basically what it gets down to is that you start with your 2 meter transmitter on the left. 10 watts, of course, way too much to drive a mixer. So we need to attenuate it down to about 1 milliwatt. And then we use some other signal source, in this case that ADF 4351 phase lock loop. Excellent choice. You can control it with the Arduino or any other simple controller. And then the mixer output, you select the 2.4 gigahertz component, amplify it, typically filter it again, making sure that your spectrum is clean, and then you feed that into your the last stage of amplification before you call it your small linear amplifier. The ADF 4351 phase lock loop board, evaluation board, Chinese ripoff that you can get relatively cheaply from China, but of course also locally here, South Africa. Anton also stocks it, and which may be quite a bit of an easier choice, no risks involved in getting hold of it. I've built one of my examples into a box, then using a bit more software, a PIC to control it, LCD to indicate the frequency, etc. Because this is not just for OSCAR100. I use it for the other microwave bands as well. Covers 35 megahertz to 4.4 gigahertz, which is very convenient if you want to play around on the other microwave amateur bands, as well as the VUHF bands. But you don't need to go to all that trouble. You can use Arduino, simple Arduino, some software from a French radio amateur, and that will control your ADF 4351 phase lock loop module that you can use for the up converter. Very simple to do. The other option, this is now quite a bit of a busy picture, but this is my current station at home, is to use a so-called headless VFO. In other words, I've got sorry, let's just go back to that one. I've got a Arduino Nano, no display, no keyboard, nothing as such. This Arduino, when I apply power, sets up the VFO or the synthesizer here to the right hand side. sets it to the correct frequency, 2256 megahertz, added with the 144 megahertz, takes you to 2.4 gigahertz where you want to be. And once it's set up, the synthesizer, it goes to sleep, switches itself off. So no possibility of spurious signals and interference being generated from the micro, especially if you've got an open setup as this one. So below my face lock loop eval board is my up converter board. And then to the left is the power amplifier. I'll show it here a little bit next a bit more. So this is a prototype phase 4 up converter. To the left, BNC socket is a 2-meter input, 10 watts. Those big resistors is they form the attenuator, taking the 10 watts down to about 1 milliwatt. I've got a variable resistor that I can use to adjust the power output level to exactly keep Layla happy. Local oscillator input, you've got the mixer, filter, amplifier, and then amplify some more, filter some more, and then eventually get the 2.4 gigahertz output. Now that 2.4 gig output, you should aim for about 100 milliwatts plus 20 dBm. Reason for that, here's another example. If you don't want to build your own up converter, it is commercially available, for example from DX Patrol. Very good product, very popular, costs a little bit more, but the people are very happy with the performance of this up converter that's commercially available from Europe. Principles are the same. Also attenuator at the top and your local oscillator, etc. If you look at the power amplifier, because you're aiming for between 1 and 2 watts to your dish. So a typical Chinese 5 watts will easily and very linearly give you between 1 and 2 watts, which is good enough for single sideband or the narrowband transponder. You can import it from China, or you can of course get it locally once again, quite easily to do. But take note here, gain is 13 dBs, not 17 or 20 or whatever they like to claim on the package. Now that's a typical gain. So that is why your up converter, you should aim for at least the output level of 100 milliwatts to get to between 1 and 2 watts out from your power amplifier, and also to compensate a little bit for the cable runs or the cable losses. So yes, don't trust those that claimed 17 dB. You may need a little small driver amplifier between your up converter and the power amplifier as well, if you don't drive it hard enough. But this is very convenient. It's got automatic RF switching, so you don't need to do anything, control it, anything like that. It automatically senses there's an input signal, amplifies it. In other words, it goes between transmit and receive. And then when you are listening, it will go back into the receive state. And that is quite adequate for our applications. Of course, seeing that we now the digital generation, you can use an SDR transmitter. So one example is the hack RF. Of course, there are others available as well. But the output level is typically quite low, looking at less than, say, 10 milliwatts. So you need another amplifier stage between this SDR transmitter to get you closer to 100 milliwatts. That will then be quite adequate to feed the your power amplifier to get you between 1 and 2 watts that you would typically require. But yes, it is a very good option as well. You can, of course, use it for the other amateur bands, 1296, 70 centimeters, and everything in between. Example of my station, or a previous version of my station, where I've used separate transmit and receiving antennas. To the left, these are just commercial dishes that you can buy for a couple of £100 each at your DSTV outlet. To the left is my receiving one. You just see a little bit of the LNB sticking out as it's mounted. The right hand side is my transmitting dish. I've got I think it's between 3.5 turns, and the latest one is probably 4.5 turn helix on the transmitting side there that goes to the power amplifier. So that's a homebrew helix antenna that I've built there. But that's adequate. This is now facing north here from my house, very close to due north, and working very well. Little effort, and that's a reward that you get, a very convenient sort of ground station. So yes, that is in short a easy approach, a low-cost approach, getting onto Quebec OSCAR100. Start with the receiving side, learn all the lessons to be learned, aiming the dish, getting the elevation set correctly, all of that. And once you can easily receive the dish or receive the downlink signal, then you can move up and get the transmitting side going as well.